Now, this session is meant to give the working knowledge of computer vision tools and techniques. Here you learn about two different kinds of object detectors, that is the reason-based and one-shot detectors. Now, this reason-based detectors are not widely used in today's world and hence will be covered very briefly. Then you learn about one-shot detectors in detail and will also implement various real-world cases using these pre-trained models. And then we will be building a custom YOLO detector to solve the task of detecting people with a face mask in the images. So let's get started with this reason-based detectors. So basically this reason-based detectors are currently not used in industry because of their slow speed, which is not suitable for real world problem. So what is this reason based convolutional neural network? So we know that object detection consists of two separate tasks, that is the classification and localization. Now this RCNN stands for reason based convolutional neural network, and the key concept behind RCNN series is reason proposals. So this reason proposals are used to localize objects within the image, and there is a difference between RCNN and YOLO. So YOLO or one shot detector runs a lot faster than the faster RCNN or other reason based detectors because of its simple architecture. So unlike faster RCNN, it is trained to do classification and bounding box regression at same time. So what are the limitations of this reason-based detectors? So even though the number of reasons are reduced to 2000 per images in case of RCNN, it takes an enormous amount of time to classify these reasons, and it is not possible to implement for real-time applications because it takes 47 seconds to predict for a new text image. So let's understand this object detection first. Now this object detection, so we all have spent plenty of time looking for objects like a TV remote, cell phone when it's on silent mode, keys and much more. So it happens to all of us and is one of the most frustrating experience. But what if a simple deep learning algorithm could locate that for you in a matter of milliseconds? So this is where the magic of object detection enhance, making our lives becoming simpler. So this computer vision industry is projected to hit $48.6 million by 2022, and now it has reached to $60 million, ranging from video collaborations, medicines to education security and many more. So from counting traffic on roads by counting vehicles present to self-driving cars, this industry has massive potential in future. So detecting people not wearing masks and regulating the social distancing in public places, object detection has gained great momentum in times of previous pandemic as well. So what is this object detection? So whenever we humans look at the image or video, we can instantly recognize and locate the object of interest. And the goal of object detection is to replicate this human intelligence. So this object detection is a general term used for the collection of computer vision related tasks to identify objects. That is, it has instance segmentation, object localization, as well as classification. Now, what is this instance segmentation? So, instance segmentation means you are partitioning a digital image into multiple segments in order to represent into something more useful and easy to analyze. Then there are certain techniques for instance segmentation like thresholding methods, edge detection, reason-based and clustering-based techniques. Then comes object localization, means you are localizing the object in an image within these confined boundaries. Then comes object classification, that is predicting the type or class of the object localized in the image. And then comes object tracking, that is you are locating a detected object in image or real world using a bounding box. Now there are certain data sets to be worked upon for this object detection. So first can be MNIST dataset, that is the Modified National Institute of Standards and Technology dataset, which is a dataset of handwritten digits for trying learning techniques and deep recognition pattern, and its size is about 50 MB. Then there are other datasets like Fashion MNIST dataset. Then we have CIFAR 10 dataset, which consists of 60,000 images of 10 classes. Then we have MS COCO dataset, which is a large scale object detection segmentation capturing dataset. Then we have ImageNet dataset, which is a dataset of images that are organized according to WordNet hierarchy. Then we have Pascal Vogue dataset, which is a well-known dataset for object detection classification. and segmentation of objects, and it has 8 different challenges spanning from 2005 to 2012. Now next comes this object detection with the bounding box. So we know whenever an image is input to the CNN, the problem of classifying the class corresponding to that image is called image classification. And as shown in this figure, the probability values for all target classes are the output. So you can think of object detection as a problem in which image classification task has a regression task that predict the position of objects using a bounding box. So problem of object detection has assumed that multiple classes of objects may exist in an image at the same time. And we can also visualize this like two types of problems. One is multi-label classification, that is multiple classes in one image, and then a bounding box regression problem in which we have to predict the coordinate values of these bounding boxes in terms of x, y, w and h. Then comes the object localization. Now the task of object localization is to predict the object in an image as well as its boundaries. And the difference between object localization and object detection is simply that the object localization aims to locate the main object in the image, while object detection tries to find out all the objects and their boundaries. Now an image classification or image recognition model simply detect the probability of an object in the image. In contrast to this, object localization refers to identifying the location of object in the image. So an object localization algorithm will output the coordinates of the location of object with respect to the image. And in computer vision, the most popular way to localize the object in an image is to represent its location with the help of bounding boxes. Now this bounding box can be initialized using the following parameters. First is bx, by, that is the coordinates of the center of bounding box. Then bw, it is the width of the bounding box with respect to the image width. Then we have bh, that is the height of the bounding box with respect to image height. Now by predicting this, they are calculating the mean IOU and then predict the bounding box, which is to do localize the object in the image. Then comes this bounding box or the losses there. So basically there are two types of losses, L1 and L2 loss function, and also we have an intersection over union region is there. Now this intersection over union region is considered to be most widely used performance metrics. Basically it is the area of overlap between the predicted segmentation and the ground truth divided by the area of union between the predicted segmentation and the ground truth, and it varies between the 0 and 1. And for this L1 and L2 loss functions, so basically this L1 and the L2 loss functions are two loss functions which are used to minimize this error. So we'll discuss in detail in the later half. Then comes this bounding box augmentation for the object detection. So here we know these bounding boxes are rectangles that mark objects in an image, and there are multiple formats of this bounding box annotation, and each format uses a specific representation of bounding box. So it can be either Pascal-Vogt, argumentation, and like it can have the COCO sets. So these are the types of the coordinates. Like the bounding box has this coordinates xy coordinates of its corner. Top left is x min, y min, that is the 98 px or 345 px is there. Then we have the top right is x max, y min, that is 420 or 345. Then bottom left is x min, y max, and then bottom right is x max and y max. So using these techniques we can find out its values like this according to the type of annotation format which we want to use for this object detection. Then comes this L1 and L2 loss functions. So this L1 loss function stands for least absolute deviation, and L2 loss function stands for least square error. Now this L1 loss function is used to minimize the error, which is a sum of all absolute differences between the true values and the predicted values. And this L2 loss function is used to minimize the error, which is the sum of the square differences between the true value and the predicted value. So how do you decide between this L1 and L2 loss function? So generally this L2 loss function is preferred in most of the cases, but when the outliers are present in the data set, then we prefer L1 loss function, because at that time this L2 loss function does not perform well. The reason behind this bad performance is that the data set is having outliers, then because of the consideration of the square differences, it leads to much larger error. So hence L2 loss function in case of outliers is not useful. So prefer L1 loss function as it is not affected by the outliers, or remove the outlier and then use this L1 loss function. So the key takeaway from this is that if this intersection over union score is greater than 0.5, then it is considered a good annotation. Also, this L1 loss function is not affected by the outliers. Now next comes this YOLO, or the you only look once algorithm. So basically it is a state of the art deep learning algorithm that is prominently used for object detection purposes. So the fact that makes YOLO quite different from other convolutional neural networks used for object detection is that it is very fast in detecting the objects in real time. So YOLO involves inputting the whole image at once, and then the image passes through the convolutional network only for one time. And this is the main reason behind naming it as you only look once. So in the other algorithm, this process happens again and again. That is, the input image passes through the CNN again and again, and which gives a really high speed object detection advantage to the YOLO algorithm over other algorithms. So imagine a car equipped with a self-driving feature that is using a normal CNN object detection algorithm. Now the car would brake itself when the algorithm would observe an obstacle in front of the car. Now here the algorithm is going to be slow, and it would notice the object as an obstacle quite late. It could easily lead to an accident. Now imagine the same condition with YOLO algorithm. So this time the car is equipped with YOLO algorithm, so it will stop well in time, as it would detect the obstacle very swiftly in real time. So how does this YOLO work? So basically this YOLO algorithm has already been trained on a particular kind of data set that consists of 80 different kinds of classes, and the list of classes is here. So here the YOLO algorithm is capable of detecting all these 80 kinds of objects in an image. It could be also be trained in a custom manner to detect new variety of objects very easily. And the dataset has been trained for the 80 classes is quite famous by the name of COCO dataset. And we'll talk about the working of YOLO algorithm in very brief and less complicated one, as this session is a beginner friendly one. So here, first an image that has been input in the network is divided into the grid lines. So here we will take an example of 3 cross 3 grid matrix. So the image is given a 3 cross 3 matrix format, and there are a total of 9 grids in this picture, and each grid had some parameters. If we suppose the total number of classes for which we are looking in the picture is 3, so supposing person, car and plane, then each grid would have a total of 8 parameters. Now how come there are 8 parameters? It is because each grid takes 5 more parameters including the 3 classes, and the 5 parameters are listed like box coordinates, objectness score, class scores. So now we only comment about these parameters when we know that what are bounding boxes. So while preparing the training data sets, we have to highlight the object that we actually want to detect in the image, and we do this with the help of bounding boxes. So basically there are squares or rectangles that highlight a specific part of the image. So here we want to detect the cars in the image, so we put the bounding box around all the cars present in the image. Now we have to know that what were those 5 parameters that belongs to each grid in the 3 cross 3 grid image. So we have one more picture here in which we have taken one particular grid where a car is actually present. Here the red dot at the middle of the center of the bounding box, the horizontal blue arrow is the parameter Tx, that is the distance between the red dot and the leftmost part of the grid. Then we have vertical blue arrow, that is the Ty, that is the distance between the red dot and the uppermost part of the grid. Then we have horizontal white arrow line is the width of the bounding box with respect to the grid and is stated as TW. Then we have vertical white arrow line, that is the height of bounding box with respect to the grid and is stated as TH. Now this parameter PO, also known as objectness score, is the probability of detecting an object successfully in a particular bounding box. And yes, here the value of 0.99 will be there. Then the class code P1, P2, P3 tells us the probability of that object, whether it's a person, car or plane. So all the 9 grids present in this 3x3 matrix have 8 parameters, and there are 8 parameters that helps the Euler algorithm to detect the objects accurately. Next comes this non-maximal suppression. Now these objects in the image can be of different size and shape, and to capture each of this perfectly, object detection algorithm create multiple bounding boxes, that is in our left image. So ideally for each object in the image, we must have a single bounding box, something like this image on the right. So to select the best bounding box from the multiple predicted bounding box, this object detection algorithm use non-maximal suppression. And this technique is used to suppress the less likely bounding boxes and keep only the best one. So we now understand why do we use non-maximal suppression. So basically the purpose of non-maximal suppression is to select the best bounding box for an object and reject or suppress all other bounding boxes. So here the objectness score is given by the model and the intersection over the union of the bounding boxes. So you can see the image along with the bounding boxes. The model returns an objectness score. Here, now this score denotes how certain the model is that desired object is present in this bounding box. So you can see all the bounding boxes have the object, but only the green bounding box is the best bounding box for detecting the object. So now how can we get rid of other bounding boxes? So the non-maximal suppression will first select the bounding box with the highest objectness score and then remove all the other boxes with high overlap. So here in this image, we select the green bounding box for the dog since it has the highest objectness score of 98% and remove the yellow and the red boxes for the dog because they have high overlap with the green box. And the same process goes for the remaining boxes. This process runs iteratively when there is no more reduction of the boxes. And in the end, we will be left with the following results. So that is it how the non-maximal suppression works. So to solidify our understanding, let's look at the steps for this implementation of non-maximal suppression. So suppose you want to build an object detection model to detect the following: dog or person. This object detection mod has given the following set of bounding boxes. So first you will select the box with the highest objectness score. Then you will compare the overlap or the intersection of union of this box with other boxes. Then you will remove the bounding box with the intersection over union less than 50%. Then move to the next highest objectness score and then repeat the processes. Then comes the anchor boxes. Now this YOLO can work well for the multiple objects where each object is associated with one grid cell. But in the case of overlap, in which one grid cell actually contains the center point of two different objects, we can use something called anchor boxes to allow one grid cell to detect multiple objects. So in this images, we see that we have a person and a car overlapping in the image. So the part of the car is obscured. We can also see that center of both the bounding boxes, the car and the pedestrian, falls in the same grid cell. Since this output vector of each grid cell can have only one class, then it will be forced to pick either the car or the person. So but by defining these anchor boxes, we can create a longer grid cell vector and associate multiple classes with each grid cell vector. So these anchor boxes have a defined aspect ratio and they try to detect objects that nicely fit into a box with that ratio. For example, since we are detecting a wide car and a standing person, we'll define one anchor box that is roughly the shape of the car, and this box will be wider than it is taller. And we'll define another anchor box that can fit a standing person, which will be taller than it is wide. So the test image is first broken up into the grid and the network then produces output vectors, one for each grid cell. And these vectors tell us if the cell has an object in it, what class the object is and the bounding box for the object. So since we are using two anchor boxes, we'll get two predicted anchor boxes for each grid cell. So sometimes, in fact, most of the predicted anchor boxes will have very low PC, or the probability of object being present in it. So after producing these output values, we'll use non-maximal suppression to get rid of unlikely bounding boxes. So for each class, non-maximal suppression gets rid of bounding boxes that have probability of object being value lower than some given threshold. Then comes the single shot detector. Now this single shot multi-box detector is a deep learning model used to detect objects in an image or from the video source. So this single shot detector basically has two components, and they are the backbone model and the SSD head. Now this backbone model is a pre-trained image classification network as a feature extractor. So usually the fully connected classification layer is removed from the model. And this SSD head is another set of convolutional layer added to this backbone, and the outputs are interpreted as the bounding box and the classes of the object in the special location of the final layers activation. So instead of using a traditional sliding window algorithm, SSD divides the image as grid, and each grid cell responsible for detecting objects in that region. So if there is no object detected, then we'll say it as a nothing, or to be more precise, we'll say it as 0, indicating that there is no object. So what if there are many objects? This is where the anchor box come in. So anchor boxes are simple boxes that are designed with multiple anchors, which are predefined and have fixed size and shape within this grid cell. So this is how will work. Now how do this single shot detector basically works? So basically the single shot detector is based on the use of convolutional networks that produces multiple bounding boxes of various fixed sizes and scores. The presence of objectness class instance in those boxes, followed by the non-maximal suppression step to produce the final detector. So here the SSD model works as follows. Each input is divided into the grids of various sizes, and at each grid the detection is performed for different classes and different aspect ratios, and a score is assigned to each of these grids that says how well an object matches in that particular grid, and non-maximal suppression is applied to get the final detection from the set of overlapping detectors. So this is the basic idea behind this SSD model. So here we'll use different grid sizes to detect objects at different sizes. For example, look at this image below. So where we want to detect the cat, smaller grids are used. But when we want to detect a dog, the grid size is increased, which marks the SSD more efficient. So let us deep dive into more details. So here basically we have the detections using multi-scale feature maps. Now this multi-scale feature maps are added to the end of truncated backbone model, and this multi-scale feature maps reduce in size progressively, which allows the detections at various scales of the image possible. So the convolutional layer used here vary at each feature layer. Then we have detection using convolutional predictors. So here the addition of each extra layer produce a fixed number of predictions using the convolutional filters. And these extra layers are shown at the top of the model in the given diagram. So for example, a features layer of size m cross n with p channels. So the minimum prediction parameters that gives a decent detection is 3 cross 3 into p, the small kernel size. Then we have default boxes and aspect ratios are there. Now these default boxes are associated with every feature map cell at the top of the network. So for each box out of k at the given location, C class scores are computed and 4 offset relatives to the original default box, which results in a total of C plus 4k filters which are applied around each location. And this allows the usage of different default boxes shapes in various feature maps. And then we have a comparison between the YOLO and SSD. So we know that YOLO, or you only look once model, is a predecessor to the SSD model, and it also detects images in a single pass because it uses two fully connected layers, while this single shot detector uses multiple convolutional layers. Now this single shot detector adds several feature layers to the end of the base network, which predicts the offset to a default box of different scales and aspect ratios and the associated scores. And also this single shot detector produces an average of 8732 prediction per class, while YOLO produces only a 98 predictions per class. And the single shot detector with 300 into 300 input size significantly outperforms this 448 into 448 YOLO part. Now we in terms of the performance, SSD model is proven to show better results than this previous state of art methods like YOLO and faster RCNN. So the multi output layers at different resolutions have impacted the performance. In fact, even removal of few layers resulted in a decrease in accuracy by 12%. So to conclude this, we can say SSD model is one of the fastest and efficient object detection model. Now here comes a diagram which shows the intersection of our union. So here we know that intersection over union is the area of overlap by area of union. So in case its value is greater than 0.5, then we consider it as a good object detection. Then these are the key takeaways from the words discussed, that SSD detector is faster than YOLO. Also, YOLO provides higher accuracy compared to single shot detector. Thank